Over 8 billion tons of plastic waste are quietly turning the ocean into the largest landfill on the planet. Waves that once carried the taste of sea salt now carry the traces of human indifference left behind. But Boyan Slat refuses to accept that reality. From the idea of this young engineer, the nonprofit organization The Ocean Cleanup was born, and in just over a decade, it has removed more than 45 million kilograms of plastic waste from oceans and rivers around the world. Yet far offshore, where currents, winds, and waves are constantly changing, what allows such a massive system to operate reliably? Is the ambition to clean the ocean, driven by a young man from the United States, truly achievable? And how exactly are they doing it? Let's find out. Every year, more than 20 million tons of waste flow into the ocean, and nearly 80% of it is plastic, a material strong enough to survive underwater for hundreds of years. Over time, these plastic fragments build up into massive floating garbage zones and slowly enter marine ecosystems, moving through the food chain and harming more than 700 ocean species before eventually affecting humans. However, environmental organizations point out that this waste is not entirely worthless. If collected and processed properly, much of it can be turned into useful resources, from recycled plastics and engineered fibers for the textile industry to recovered metals. This recovery process saves thousands of kilowatt-hours of energy, reduces millions of tons of CO2 emissions, and helps create a circular ocean economy where discarded materials are given a new purpose and a new life. The process of collecting ocean waste begins with a fundamental but extremely difficult challenge: how to retrieve massive volumes of debris in constantly changing open sea conditions. In major accumulation zones such as the North Pacific Gyre, countries are forced to deploy specialized industrial-scale cleanup systems. At the core of these systems are dedicated cleanup vessels, which function as floating industrial platforms on the ocean. Each vessel is equipped with two hydraulic mechanical arms extending outward from both sides, sweeping across the water in a wide fan-shaped pattern to capture drifting debris. From plastic bottles and bags to abandoned fishing nets, the collected waste is guided into floating channel systems connected to the ship, then transferred onto stainless steel conveyor belts mounted on the deck and deposited into large holding compartments. A single cleanup cycle typically lasts between 8 and 10 hours and can process 5 to 10 tons of mixed marine waste per operation. Not all discarded waste makes its way into the open ocean. A large portion becomes trapped in rivers, reservoirs, and canals, where it builds up into dense layers that restrict water flow. In these environments, compact mechanical equipment is deployed, most commonly clamshell excavators mounted on dump trucks. Each steel bucket, weighing nearly 1,000 pounds, can reach deep below the surface to scoop up mixed debris. Plastic bottles, bags, branches, and even old tires. Every lift can remove between 500 and 1,000 pounds of trash, and with hydraulic power, a single crew can clear a river section hundreds of feet long in just a few hours, nearly 10 times faster than manual cleanup. However, in many coastal regions, collection still relies on local fishermen and volunteers who use small nets and hooks from their boats under the scorching sun. Each person may retrieve only a few hundred pounds of waste per day, but their efforts represent the essential first step in the ocean's recycling chain. After the offshore collection stage is completed, the recovered waste is transported back to shore by trash skimmer vessels, specialized boats designed specifically to capture floating debris. A compact skimmer, measuring roughly 25 to 30 feet in length, can collect up to 5 tons of material during an 8-hour operation. Once its storage compartment is full, a hydraulic conveyor at the bow lifts and discharges the entire load into the receiving area on land. At this point, the preliminary sorting phase begins. The freshly offloaded mixture contains a wide range of materials, including plastics, metals, wood, seaweed, and organic sludge. Workers perform a rapid inspection to remove oversized or hazardous items, such as steel nets, oil buoys, and tires. The remaining material is then fed onto a conveyor belt that carries it into the screening system. Inside the sorting line, a trommel drum separates the waste by particle size. Sand, silt, shells, and small fragments fall through the perforations while bottles and packaging remain inside. This remaining stream, composed mainly of plastics and nylon, moves onto a manual sorting belt, where workers separate each category in preparation for the next stage of recycling. Once detailed sorting is complete, materials such as metal, glass, and wood are sent to their dedicated processing lines. Plastic, however, the planet's most durable yet most problematic material, is set aside to begin its path toward renewal. Join the Factor as we explore how humanity transforms drifting marine debris into reusable resources that support a more sustainable future. After the recyclable portion of the waste, mainly plastics, nylon, and metal cans, is separated, it moves into the washing stage, a critical step before recycling can begin. Ocean debris typically spends long periods submerged in salt water and becomes coated with algae, oils, and microbial growth. Inside the processing area, the material enters a mechanical wash tank, where rotating shafts fitted with paddles create turbulent flow that scrapes off surface buildup and rinses away impurities. The wash solution contains mild cleaning agents and a chloride neutralizing compound to remove salt and oil residues. In some facilities, hot water ranging from 160 to 180 degrees Fahrenheit is used to enhance sterilization. This cleaning phase usually lasts between 15 and 30 minutes, depending on contamination levels. Once cleaned, the materials move into a drum washer, which rotates while blasting them with high-pressure water jets to remove stubborn sand and algae. A float sink tank then separates plastics by density. PET sinks to the bottom, while HDPE and PP remain afloat, ensuring proper separation before recycling. The freshly washed material is transferred to a centrifugal dryer to remove remaining moisture, followed by hot air drying at around 170 degrees Fahrenheit. In larger facilities, ozone-based deodorizing systems are added to treat vapor emissions, eliminating organic odors and neutralizing bacteria. At the recycling facility, plastic does not move straight into processing. Instead, it enters a screening stage designed to decide what is worth saving and what must be removed. While the industry recognizes 7 major plastic families, the system focuses on 2 of them, PET and HDPE, because they deliver the highest recovery value. Everything else is gradually filtered out. The remaining plastic is fed into a slowly rotating steel drum, where gravity and motion do the first round of separation. Fine debris such as dust, sand, and small fragments escape through perforated openings, while intact bottles stay inside and continue forward. By the time the material exits the drum, it has already been simplified into a more manageable stream, reducing stress on the machines that follow. From there, the flow passes on to a sorting conveyor monitored by workers who remove non-plastic items like metal cans, cardboard, and stray nylon. An automated system then targets caps and labels, using high-speed vortex air to peel away attached components. Magnetic scanners continuously check the line, ejecting even the smallest metal residues. What remains at the end of this stage is no longer mixed waste, but a consistent stream of clean PET bottles. The main body of each plastic bottle is next fed into a high-speed grinding system. Inside the enclosed chamber, hundreds of hardened alloy cutters rotate at extreme speeds, rapidly breaking the bottles down into small plastic flakes. In a single hour, one granulator is capable of processing roughly 2,000 to 3,000 pounds of material, converting bulky piles of bottles into a continuous, uniform stream. These flakes, measuring only a few inches across, are small enough to pass smoothly through downstream thermal systems without clogging equipment. Beyond reducing volume, this size reduction significantly improves energy performance in later stages. Once fragmented, the plastic melts far faster inside the extrusion unit, lowering electricity consumption by as much as 40% compared to melting solid plastic pieces. At the same time, granulation establishes the first layer of size consistency, ensuring the feedstock remains uniform before entering the next phase of precision: separation. At this stage, precision sorting moves to a microscopic level. Advanced optical scanners equipped with high-speed sensors analyze every plastic flake individually, evaluating color, transparency, and surface features in fractions of a millisecond. When the system identifies a clear PET flake, a green PET piece, a white HDPE particle, or a contaminant such as wood or glass, a carefully targeted burst of compressed air instantly redirects it out of the main flow. A single sorting unit can process more than 1,000 particles per second while maintaining accuracy above 95%. Each air pulse is calibrated to strike only one tiny fragment, weighing less than 1,000th of an ounce, without disturbing surrounding material. By the end of this process, the output is a clean, uniform stream of plastic flakes, precisely separated by type and ready to serve as the feedstock for the pelletizing stage that follows. Once approved, the plastic flakes are fed into an industrial-scale extrusion system. Inside the unit, the material is heated to around 520 degrees Fahrenheit, causing it to melt and advance along a heavy-duty rotating screw. As internal pressure rises, the molten plastic is pushed through an ultra-fine metal filter that traps any remaining impurities. The purified melt then enters an underwater pelletizing line, where it is immediately sliced into millions of microscopic beads known as pellets. A closed-loop cooling system rapidly solidifies each pellet at the moment of cutting, ensuring uniform size and a smooth surface finish. These pellets form high-grade industrial feedstock, ready to be used in manufacturing packaging, synthetic textiles, or even molded into entirely new bottles, completing the transformation from discarded waste into a valuable raw material. Using recycled PET pellets as input, the production line shifts into the preform manufacturing stage, where bottles begin as partially shaped components rather than finished containers. The material is first inspected for uniformity, then fed into an injection molding system. Inside the unit, the plastic is heated to approximately 480 degrees Fahrenheit until it becomes pliable. In this softened condition, the molten resin is injected into precision steel molds, forming short, thick-walled tubes with threaded necks already configured to accept bottle caps. Each preform is designed to withstand elevated temperatures and internal pressure, allowing it to remain stable during handling, transport, and the reheating process required for blow molding. Thanks to their compact shape, preforms can be stored and shipped efficiently over long distances. Many manufacturers specialize solely in producing these components, supplying them to bottling facilities closer to consumers, where the preforms are reheated and expanded into their final bottle form. In the next stage, the preforms are reheated until the plastic becomes flexible, taking on a rubber-like consistency. They are then fed into a stretch blow molding system where high-pressure air is injected through the neck, forcing the softened material to expand and conform tightly to the inner walls of a bottle-shaped metal mold. A preform measuring just 4 to 5 inches in height can elongate to nearly 4 or 5 times its original size during this process. Once molding is complete, each automated line can generate thousands of bottles within seconds, while maintaining an extremely low defect rate. Laser-based inspection units continuously check wall thickness, symmetry, and optical clarity to ensure consistent output. Beyond standard bottle formats, the system can fine-tune volume, contour geometry, and label alignment to meet individual brand requirements. At the end of this stage, fully formed PET bottles emerge, ready for cooling, capping, and final packaging. Once released from the mold, the bottle remains extremely hot and vulnerable to deformation. To prevent this, the production line immediately directs it into a rapid cooling zone, where chilled air or recirculated water is applied. Although this phase lasts only a matter of seconds, it is enough to stabilize the structure and permanently set the bottle's shape. In more advanced facilities, the heat emitted by newly formed bottles is captured and reused to preheat cooling water, significantly reducing overall energy demand. After the plastic fully solidifies, the bottle gains the mechanical strength required to withstand internal pressure during filling and transportation. Cooling rates are carefully engineered to balance high output speed while maintaining optimal clarity and rigidity. Before leaving the manufacturing site, every plastic bottle is subjected to a comprehensive quality control process. Optical scanners, High-resolution imaging systems and pressure testing equipment work together to detect even the smallest imperfections, including microfractures, trapped air pockets, or dimensional irregularities. Selected samples undergo additional mechanical testing, such as tensile strength, compression tolerance, and impact resistance to verify long-term durability. For bottles intended for food and beverage use, extra chemical analysis ensures that no harmful residues remain. Only after meeting all quality standards are the bottles grouped, palletized, and sealed with protective shrink wrap. Automated palletizing robots organize thousands of units with precise alignment, assigning each batch a unique traceability code. From the main distribution hub, the finished products are shipped to bottling plants, supermarkets, and retail outlets, completing the recycled plastic life cycle. Each newly produced bottle represents more than a consumer item. It reflects the success of a circular technological system in which discarded materials are transformed into valuable resources. You've now followed the entire path, from collecting ocean-bound plastic to cleaning, processing, and returning it to the supply chain as a renewed material. What begins as drifting waste at sea ultimately becomes a resource that fuels modern manufacturing, revealing a process far more complex and impressive than it might first appear. The information presented in this video is drawn from multiple reliable sources, so if you spot anything that could use clarification or correction, feel free to share your thoughts in the comments. And if you believe recycling can help shape a more sustainable future, leave a like, join the discussion below, and subscribe to Mandarin Tech for more stories about innovation, transformation, and renewal.